We are Team Alpha, and we're continuing to develop the hydrogen aeroplane project we worked on in second year. We produced a design that generates electrical power from the otherwise unutilized thermal energy stored in cryogenic hydrogen. It works by passing the hydrogen through a heat exchanger in the wings, exchanging heat with the environment, and then passing the pressurized gaseous hydrogen through a turboexpander. To develop this further, we wanted to create a scaled-down 3D printed model of just the turboexpander to test the feasibility of the idea and test different turbine angles to find the most efficient design.
The CAD from the original design first had to be scaled down to the size of the 3D printer we had access to. Then we changed the design to use regular ball bearings rather than electromagnetic bearings, as this would otherwise add complexity to the testing. The large three-phase AC generator used was changed out to a small three-phase BLDC motor. We then connected the phases of this motor to a three-phase rectifier, which converts the voltage to DC, which we could then measure and plot using an Arduino. This analyzes a voltage waveform and determines the DC voltage along with the frequency of the wave to determine the RPM of the motor. By measuring the resistance of the rectifier, the electrical power produced by the motor can then be calculated.
Once the CAD was finished, 3D printing could begin. We first printed parts to test the tolerances between 3D printed parts and standard components, such as the shaft, nuts and bearings. We did this before printing the large main parts. This was to avoid making mistakes which could cost days in print time. Next, we moved on to printing the housing for the turbine. This was the most time-intensive part of the project, taking around a week to complete due to the large size of parts and relentless setbacks due to failed prints and minor changes in the design. To speed up the process, the main housing was split down into sections, making each part smaller and the individual print time shorter. It meant a failed print would set back the project's product by less time.
Once all the parts for the housing were printed, they were glued together using superglue to form the finished housing. To align the housing to the motor, a supportive base was designed and made from laser-cut acrylic. In our first attempt, the tolerances between the parts were too big, meaning the parts were loose. This was due to the 6mm thick acrylic sheet not having a uniform thickness. We then recut the base with smaller tolerances which made a better fit. We first tried using superglue to adhere the base together, but unfortunately the bond was not strong enough. We instead used UV curing adhesive, which created a much stronger bond.
After some further research into turbine machinery, the inlet and outlet angle for a range of 5 turbines were calculated. Our goal was to find out which turbine produced the most power for the same inlet conditions. We first tested the initial conditions, such as the pressure change and mass flow rate without the turbine inside the housing. Then we started testing with turbines. On our first test, the turbine didn't spin with or without the load from the motor. We then made the tolerances between the housing and the turbine smaller. However, this caused the turbine to scrape on the housing. Finally, we made the base of the turbine thicker to reduce the inlet surface area of the turbine. This still didn't work. After some thinking, we predicted that we needed a higher mass flow rate for the turbine to spin.
To increase the mass flow rate of the air, we decided to utilize a Venturi pump in testing. This is when the fast-moving air creates an area of low pressure around it, which draws surrounding air into the flow. This therefore increases the flow rate, which is exactly what we needed. We then got additional holes drilled into the end cap, allowing for surrounding air to be drawn in. This creates a more permanent Venturi pump.
We could now move on to testing the other 5 turbines. We recorded the outlet velocity and difference between inlet and outlet pressure and temperature. We also plotted the voltage and RPM produced by the motor using the Arduino and a tachometer to verify the RPM results. We repeated the experiment 3 times to ensure accurate results. These readings allowed us to calculate the mass flow rate, pressure ratio, and efficiency of the system in order to make a comparison between the turbine designs. From this experiment, we concluded that turbine design 3 with an outlet angle of 55 degrees was the best turbine, as it had the highest efficiency of 83.5% and the highest steady state shaft RPM, which was 560 RPM for the same inlet conditions. It produced an average power of 0.74 watts. If we could go back and repeat the project, we'd either choose a higher pressure air supply or make the turboexpander smaller. This would allow us to achieve a higher pressure ratio and reach a much higher shaft speed, giving us more conclusive data to make comparisons between the turbine designs. Thank you very much for watching.